screen recording for 8-3 day 2 and 3. Okay, it's really from 8-3 day 2. And it's some of these that if you want to go through in a slower pace, that would be fine. So we're talking about finding the volume of a solid by revolving a region trapped between a curve and a line and rotating it around that line. So the first suggestion I would make is add all your line equations, including the revolution lines equation, to your picture. What I mean by that is something like this. Add in that you've got a line at y equals 2. Add in that you've got another line or curve at y equals square root of x. Find their intersection point, add that in. Label your rotation axis. So I've got my y-axis highlighted in purple and its equation, x equals 0. That's important for us to see the various equations that we have. It will help us in a minute and what we're rotating this around. So get that labeled. We want to start to envision what this solid would look like next. Pause the video where you need to add something in to make yours really good. As we're thinking about this, that top line at y equals 2, that's going to act like a radius for that top part of the curve. And when that radius swings around, it's going to make a circle at the top. And then each line, horizontal line segment between the y-axis and that curve is going to make another set of circles underneath and underneath and underneath until it gets down to this bottom point where it isn't going to be able to rotate at all because it's sitting on the rotational axis. So a rough sketch of our solid would be a good idea in the orientation it will be in. So I've got a rough sketch of the solid, kind of funnel shaped. Your next question then is each section a stacked up disc, meaning circle filled in, or a washer, something with a hole in it? And this solid doesn't look like it's got anything missing in that cone. It looks like that's a solid cone of chocolate, a solid cone of cheese, a solid cone of whatever you'd like it to be, or funnel. It's not really a cone. So when we sketch and label that solid, we also want to think about what would those sections that are stacked up look like. And a section stacked up, think Smarties candy, think any candy that we could make this out of, that we could get smaller and smaller and smaller ones. So this is going to be a circle, or a disc as they call it. So sketch one circle or disc and label what you know about it. So in labeling what I know about my disc, I know it's going to be a circle, so that's supposed to look a little 3D, a little perspective-y. I know that the line going through it is that turning axis, that x equals 0. And since that's an x equals form, I want to get the other curve that this is formed from. Remember, the other curve that all of my circles end up meeting is that one. So I want to get my other curve in x equals form as well. They both need to be in that same format. In other words, in terms of y, since they're rotating around something that's parallel to the y-axis, or is the y-axis in this case. So our radius then comes from the fact that we have to get an x value from this function right here, and then subtract the x value from this function. As that circle moves up and down, it's still going from that function on the right to the y-axis. So the radius of each of those rings needs to go from that x equals y squared to that x equals 0. So our radius is y squared minus 0 for each of those discs as they go down. So our area for this particular circle then, pi r squared, so pi times my radius value squared. And once I have the area for each of these sections described in variable terms, now I need to think about how can I add up the areas of every single one of those to get volume. And that's where calculus comes in. And calculus says, well, the volume for solid needs to be the area multiplied by a thickness, in other words, something to turn it into volume. Think cardboard, that was our point 2, the generic thickness of cardboard. We're talking about being able to make infinitely many tiny discs like this, and so the difference in the y value, so we're integrating in terms of y because we're going around the y-axis. That means my bounds for integration need to be the highest y value that that circle ever sits at and the lowest y value that those circle discs ever sit at. So I'm integrating between 0 and 2. And you can do this by hand if it was a non-calc problem. Otherwise, I went and got a numerical approximation for its volume. So replay the video, retry the drawing yourself. That should be 106. Try the drawing yourself. The hardest part is getting them set up. The calculus will be the easy part. So hang in there.